Hi folks, today I want to talk about two aspects of the Laplace transform, its uniqueness and its linearity. And basically what I want to do is show you how the region of convergence comes into play whenever we talk about the uniqueness of the Laplace transform and we talk about the linearity of the Laplace transform. Because remember, the region of convergence is an integral part of the Laplace transform. So in order for the Laplace transform to be unique, we have to consider the region of convergence. And the same thing in terms of linearity, we have to consider the region of convergence when we talk about the linearity of the Laplace transform. And that's what we're going to do today. And the way I'm going to do this is I'm going to do it through an example. So let's take a look. So the last time we looked at the Laplace transform of e to the minus 2t u of t, and we said this was equal to 1 over s plus 2 with the region of convergence sigma greater than minus 2. Okay, so let's take a look at a Laplace transform of a different function, and this one is minus e to the minus 2t u of minus t. Now it's a very different function, though in form it seems to look the same, but it really is a different signal. The plus e to the minus 2t is this decaying exponential, right? E to the minus 2t u of t is this part of the decaying exponential. So this is e to the minus 2t u of t. E to the minus 2t u of minus t would be this part of the decaying exponential, right? So it would be this part. But then we have this minus out in front, so it's actually this. So this is e to the minus 2t u of t, and this is e to the minus 2t minus e to the minus 2t u of minus t. Very, very different functions, right? One is clearly nicely behaved. The area under it is finite, and because the area under it is finite, we can find the Fourier transform, the system. If this was the impulse response of a system, the system would be stable. In this case, just as clearly the area under here is not finite, we wouldn't be able to find the Fourier transform of this. If this was the impulse response of a system, the system would not be stable. Okay, so now let's find what the Laplace transform is. So let's write it out. That is minus e to the minus 2t u of minus t times e to the minus st dt, and the integral is from minus infinity to infinity. The u of minus t will make this the integral from minus infinity to 0. So this is equal to, I'll take the minus outside, and this is from minus infinity to 0 of e to the minus 2t e to the minus st dt. Right? So this is equal to minus from minus infinity to 0 e to the minus s plus 2 t dt, which is equal to, now this minus and this minus will cancel out, so I'll just get positive 1 over s plus 2 e to the minus, and now let me write the s as sigma plus j omega. So this is sigma plus j omega plus 2 t evaluated between minus infinity and 0. And as we did before, let's split out the real part of this. So this is e to the minus sigma plus 2t, and the imaginary part, which is e to the minus j omega t, evaluated between minus infinity and 0. When I plug in 0, I'll just get e to the power 0, which is 1. So that works out just fine. When I plug in minus infinity, this one here is not an issue, because whatever we get will have a magnitude of 1. Here, when t goes to minus infinity, this minus will cancel out with that minus. So that means I'll get sigma plus 2 times infinity. So if sigma plus 2 is positive, then I'll get e to the positive infinity, and that'll blow up. If sigma plus 2 is negative, then I'll get e to the minus infinity, and that'll go to 0. So the region of convergence is then whenever sigma plus 2 is negative, right? Because the minus here and the minus here are going to cancel out. So this is going to be equal to 1 over s plus 2. When I plug in 0, it's 1 minus 0, as long as sigma plus 2 is negative, is less than 0, or sigma is less than minus 2. Or this is equal to 1 over s plus 2 for sigma less than minus 2. All right, so let's write that out. Let's write both of them out. So the Laplace transform of e to the minus 2t u of t is equal to 1 over s plus 2, sigma greater than minus 2, and the Laplace transform of minus e to the minus 2t u of t, u of minus t, is equal to, again, 1 over s plus 2, but now sigma is less than minus 2, right? So these two functions that we showed, one of them is this nice, well-behaved decaying exponential, and the other one is this wild going to infinity function. These two are very different functions, behaving very differently. If I just looked at this part of it, then the Laplace transform of both of them would be the same, and the uniqueness of the Laplace transform goes away. So I could go from here to here or here to here. So not unique. The Laplace transform becomes unique only when you also include the region of convergence. Okay. A thing which we'll see again later on. Notice that this is a right-sided function. It's non-zero to the right of a boundary, and the region of convergence is a right-sided region of convergence, right? So if I plotted this region of convergence, it would be kind of like this. And here I have a function that is left-sided. The time function is left-sided. It is non-zero to the left of a boundary, of a point. And if I looked at the region of convergence is a left-sided, goes from some boundary all the way out to infinity, right? So those are things that we'll kind of emphasize later on as well. For now, the one thing that I want to emphasize is the fact that the region of convergence is necessary. You have to have the region of convergence if you want to talk about the uniqueness of the Laplace transform. Okay, and the Laplace transform is unique as long as you include the region of convergence. By the way, by now, this is going to be something that we'll do over and over again. So let's make it a general rule. If I have Laplace transform of e to the minus at, this will be equal to 1 over s plus a and u of t. That is kind of important. Sigma greater than minus a. And of course, all the exponents we've seen have all been real. Up in just a minute, I will show you one where it isn't real, and we'll go back to it over again. Okay, so that's it. The Laplace transform is unique if you include the region of convergence. You have to remember to include the region of convergence. Okay. The next thing I want to do is talk about the linearity of the Laplace transform. And again, linearity is kind of self-evident. After all, the Laplace transform is an integral transform. The integral operation is a linear operation. So, of course, it's linear, except that we have that ROC in there, the region of convergence. So we need to kind of take that into account. It doesn't make it not linear. It just means that we have to take it into account. So it's a linear transform. If I was taking the Laplace transform of alpha x of t plus beta y of t, then that would be equal to the integral from minus infinity to infinity, alpha x of t plus beta y of t times e to the minus st dt. And if all of these integrals exist, I could write that as integral from minus infinity to infinity. Could take that alpha out, and that would be x of t e to the minus st dt plus beta integral from minus infinity to infinity y of t e to the minus st dt. And so that would be equal to x of s, but it would be equal to x of s within some region of convergence. Region of convergence means these are values for which this function is finite, right? That's how we got the region of convergence. We found the values of sigma for which this thing doesn't blow up, okay? So x of s, we obtain x of s, but x of s is only valid over this region of convergence. And so this would be alpha times x of s plus beta times y of s. But again, y of s would only be valid over some region of convergence, and let me call that r sub y. Now, when I add these two together, both of them have to be finite. If one of them goes off to infinity, then the sum goes off to infinity. So the region of convergence has to be one that in which both x and y, both this integral and this integral converge. That is, the region of convergence is going to be the common part of r sub x and r sub y. Whatever is the region that is common between r sub x and r sub y, or the intersect of r sub x and r sub y, that'll be the region of convergence. Okay, let's take a very simple example and take a look at it. So let's say x of t is equal to 2e to the minus t plus 3e to the minus 4t. Again, I keep forgetting the u of t's. U of t, right? The Laplace transform now, if I took these individually, so 2e to the minus t u of t would be 2 times 1 over s plus 1, and the region of convergence is sigma greater than minus 1. And the Laplace transform of 3e to the minus 4t u of t will be equal to 3 times 1 over s plus 4, sigma greater than minus 4. Right? When I add these together, when I look at x of s, then x of s is the sum of these two, as long as we're in a region that includes, that's not outside of sigma greater than minus 1 and sigma greater than minus 4. Let's just plot this for a minute. So let's say this is minus 1. So this is the region of convergence for this. And here is, say, minus 4. And this is the region of convergence, right? Both of these have to exist. And they both exist in the intersect of this and this region, right? So x of s is equal to 2 over s plus 1 plus 3 over s plus 4, as long as the region that we're talking about is one in which this converges and this converges. Well, they both converge in this region, right? In this region for sigma greater than minus 1, this one converges, clearly, and so does this one. It also converges in this area, but this one doesn't converge in that area, so I can't have that. So the region of convergence for the sum is going to be sigma greater than minus 1. And for reasons that will be obvious later on, we usually prefer to write this as just a numerator polynomial over a denominator polynomial. So this is 2s plus 8 plus 3s plus 3. Well, that's 5s plus 11 over s plus 1, s plus 4, and sigma is greater than minus 1. Okay, remember that sigma greater than minus 1 is the intersect of these two. Okay, so whenever you talk about linearity, you have to worry about that. Okay, so I said, we've been doing these things where we have these exponentials, but the exponents are always real. Let's do a problem where that is not the case. So let's take this. Let's get a new paper because this will take a little bit. Let's suppose I have x of t is equal to e to the minus 3t cosine of 4t u of t. Right? And initially it looks kind of different because we've been working throughout with exponentials, and now we have a sinusoid. But a sinusoid really is just a bunch of complex exponentials, right? So we can write this as e to the minus 3t, and this will be 1/2 e to the j 4t plus 1/2 e to the minus j 4t and u of t. Or that's just 1/2 e to the, let's put a minus here, minus j. So this will be 3 minus j4t, right? I've got a positive here, minus here will make it positive. And the unit step plus 1/2 e to the minus, there's no j, e to the minus 3 minus j4, right? So e to the minus 3 plus j4t. Okay, so again, I have complex exponentials, and looks pretty much like e to the minus at u of t. And remember what we had. We had a Laplace transform of e to the minus at u of t was equal to 1 over s plus a, sigma greater than minus a. Okay. If a is complex, this part really doesn't change. You still work it the same way. This part, though, we have to change because remember, sigma is the real part of s. And if a is complex, then a real number greater than a complex number doesn't make sense. So we have to kind of look at that. And so let's do that. So let me take this one, and I'll go through and work this, and then we'll look at it. So Laplace transform of 1/2 e to the minus 3 minus j4 t is equal to the integral from minus infinity to infinity. I'll put the 1/2 out here. E to the minus 3 minus j4 t e to the minus st dt, which is equal to 1/2. Oh, there was the u of t. I always forget it. And that u of t will make this go to 0, so it'll be 0 to infinity, e to the minus, and now let's put everything together. So this is s plus 3 minus j4 t dt, and the integral will be 1/2. This is minus 1 over s plus 3 minus j4 e to the minus. And now I'll have to worry about this limit, this at infinity. So I'm going to take s and write that as sigma plus j omega. So this is sigma plus j omega plus 3 minus j4 t evaluated between 0 and infinity. Right? So that's equal to 1/2. Again, the 0 part doesn't matter because when I plug 0 in here, I'll get e to the power 0, which is 1. The infinite part matters. So in order to see what that effect is, I'm going to separate out the real and imaginary parts of the exponent. So I've got this. And here I have the real part. I have sigma and 3. So I have sigma plus 3t e to the minus, and I'll take that j out. So I have omega minus 4 t And I'm going to evaluate between 0 and infinity. Now this is e to the j something, so this will be cosine of something minus j sine of something. And the magnitude of that is always going to be 1, so I don't have to worry about what happens to this, because I know this is finite. Here, when I plug infinity in here, I have a negative sign out here, so as long as sigma plus 3 is positive, I'll have e to raised to the power minus infinity, which will go to 0. So in order for this thing not to go to infinity, I need sigma plus 3 to be positive. And if sigma plus 3 is positive, when I plug in infinity in here, this thing is going to go to 0. So I'll get 1/2 minus 1 over s plus 3 minus j4. And I plug in infinity, this goes to 0. Plug in 0, this goes to 1. As long as sigma plus 3 is positive, or sigma plus 3 is greater than 0, or sigma is greater than minus 3, right? I'm comparing a real number with a real number. Or I get 1/2 times 1 over s plus 3 minus j4, sigma greater than minus 3. Okay, that's the first. So we had two complex exponentials here, this one, and we just found the Laplace transform of this one. We can also find the Laplace transform of this one doing the same thing. So this is the Laplace transform of 1/2 e to the minus 3 minus j4 t u of t. And now if I look at the Laplace transform of 1/2 e to the minus 3 plus j4 t u of t, I'll get, this will be, again, I have e to the minus at u of t, so I'll get 1/2 1 over s plus a, so this will be 1 over s plus 3 plus j4. And the region of convergence will only depend on the real part, right? So again, I'll get sigma has to be greater than minus 3, right? So combining these two, the Laplace transform of, I started out with e to the minus 3t cosine of 4t u of t is equal to 1/2 1 over s plus 3 minus j4 plus 1 over s plus 3 plus j4, and sigma is greater than minus 3. So I have to have sigma greater than minus 3. Or that is, let's see, let's just do it. S squared plus 3s plus j4s, and then plus 3s again, plus 9 plus j12 minus j4s minus 12j and then minus j squared 16, so it's plus 16. And then above I'll have s plus 3 plus j4 plus s plus 3 minus j4. And of course, sigma is greater than minus 3. So if I put it all together, I get 1/2 times 2s plus 6 over s squared plus 3s and 3s, 6s. And this cancels out with this, and this cancels out with this, And I've got 9 plus 16, so it's plus 25, or s plus 3 over, and I might have made a mistake in here somewhere, s squared plus 6s plus 25, as long as sigma is greater than minus 3. So it was a bit messier, but the process was exactly the same. You still have e to the minus something, e to the minus something times t. That something became complex when you multiply it with a cosine. Okay, I got one last one that I want to show you, and then I'm going to let you be. Because here the region of convergence is a little bit different again. So let's take a look at this. So let's suppose this is 1 and this is 1. And so I've got an x of t that is finite, has a finite value or a finite region. Now, up till now, everything that we've been doing has been, so I had e to the minus 2t u of t, which went like that all the way out to infinity. I had minus e to the minus 2t u of minus t that went all the way out to infinity. I had e to the minus 3t multiplied by cosine 4t, which again went all the way out to infinity, so it was non-zero over an infinite range. This one is the first one that we have, which is finite over a finite range. So the range is finite. In these cases, the range over which the function is non-zero is infinite. Here, the range over which the function is non-zero is finite. And so I can take the Laplace transform is really simple. So the Laplace transform is, remember, minus infinity to infinity, x of t, e to the minus st dt. This thing has only values between 0 and 1, so this becomes an integral between 0 and 1. In that range, x of t is just 1, so x of t is just 1, and we'll get left with e to the minus st dt. So that's minus 1 over s, e to the minus st, evaluated between 0 and 1. Now here is where we started, we had to worry about the region of convergence, because we would have a limit that was infinite, and when we plugged that in, this thing would either blow up or go to 0. We had two choices, and in order for it not to blow up, we had to figure out what are the values of sigma for which this integral doesn't blow up. In this case, we don't have that problem. We can plug in either 0 or 1, and everything is just fine. Nothing is going to infinity. So I can just write that as minus 1 over s. Plug in 1, I'll get e to the minus st. Plug in 0, I'll get e to the power 0, which is 1. Or I can write that as 1 over s, 1 minus e to the minus st. And the region of convergence for this is all of the s-plane. So I can write this for all s, or I can write this for all sigma. It's pretty much the same thing. However you want to say it. For all values of s, this is finite. Okay. Some of you might look at it and say, wait a minute, I mean, when s is equal to 0, this is going to blow up. But it doesn't. And you can try it out. You know, if you think about it, this is just 1 minus e to the minus st over s. When s is 0, the denominator is 0, but the numerator e to the power 0 is 1. So I've got 1 minus 1 is 0. So the numerator is 0 and the denominator is 0. So, you can use L'Hopital's rule and you'll find out that it doesn't blow up. But what we have is that this function has a region of convergence that is the entire s-plane. And this function was different from the other functions that we saw in that it was non-zero over a finite range. Okay, and we'll come back to all of this in later modules. But so the two main things. One, the Laplace transform is unique as long as you take into account the region of convergence. You have to take into account the region of convergence. If you take into account the region of convergence, the Laplace transform is unique, and the Laplace transform is linear, so I can take the Laplace transform as a sum to be the sum of the Laplace transforms as long as I keep in mind the fact that the region of convergence has to be the intersect of the region of convergence for each of the terms. Right? If I have x of s and y of s, then the region of convergence for x of s plus y of s has to be the intersection of the region of convergence for x and the region of convergence for y. Okay, and those are the two things that are the points of this module.